261. This is what I'm saying. These are the worksheets we've been working on to get you to the book level. I'm going to go here, squeeze theorem. Okay, I'm going to import this into Notability for you. Because if you look at the study guide, you go, hey, what about this thing called the squeeze theorem? And it's a very simple concept and idea and really easy to use. You can't use a squeeze theorem for everything, though, so don't even try it. There's only like 4 examples or 4 questions on your book that are squeeze theorem, and it even tells you use the squeeze theorem, I believe. So I'll do the same. I'll say, hey, use the squeeze theorem because you might like it so much you think you could use a squeeze theorem on everything, but you can't. And it's very special, and let's talk about it, right? So here's the big thing that you want to know. You got this h of x function smaller than f of x, which is smaller than g of x. So I look at this as the smallest, the middle, and the largest. And these are really y values, okay? Because y is f of x, y is h of x, y is g of x. And then they say, look at these values for x near what? X near a. So you're looking at for the values of x near a. So this situation is occurring for the values of x that are near. And being near doesn't mean being at. Okay, so you might say, what does that mean? It does have a specific math meaning, but in this picture here, this is where your a value is. And, you know, I stole it. I can actually do my own version. I'll probably change it in the future, but I was pressed for time. Anyway, and so what you're seeing is for the values of x that are around this a value, being near, this h, f, and g, the further the elevation is, the larger the y value, right? These are all those corresponding kind of y values, if you want to think of it that way. And that's happening to the left. It's also happening to the what? To the right. For x somewhat near a. So if you have the h, f, and g smaller, middle, larger for the values of x near a, and you know the limit of what? H equals the limit of g is that finite number L. So remember, this is the smaller function and the larger function. You know the limit of both of those functions, they're L. And that's kind of what you see in this picture here, the red curve and the green curve. Okay, around A. What does that force the limit for f to be? Also L. This is known as the squeeze theorem, and we just show you a picture of the situation. And all right, and show you examples of the situation. Okay, now here's kind of what's going on. Here's the squeeze theorem. You see this first picture. And notice I didn't even write anything. I mean, I guess I could have, but maybe I will in the future if I expand on this. I'll think about that. What's the limit as x goes to 0 of x squared sine pi x? Well, here's what you guys want to know. For the first 4 questions, you got to go back to trig. Meaning, if I asked you, what do the sine values live between? Sine lives between what? -1 and what? +1, okay? It's based on this idea. That's an absolute value inequality, but sine, the output values of sine, those y values, live between -1 and +1. Are you guys okay with that? If you ever had a graph sign, you go, oh yeah, I remember that stuff. Okay. Now, if I said to you, what's the effect of multiplying an inequality by a positive number? You say, what do you mean? If I multiply the left side by an x squared, the right side by an x squared, the middle, left and right, because x is positive, I take that back. X squared is positive. X could be positive or negative. And what I'm saying here is you're just not letting x be 0, but the point is negative x squared is less than or equal to x squared. I'm going to change that from sine theta, but just say sine x, because it doesn't matter if it's sine theta or sine x. What I want you guys to know, or even in this example, pi over x, what I want you guys to know is that they ask you to use squeeze theorem here, and this is how you guys use it. Okay, because this is the f right in here. This is that f function. This is what is it, g? No, h. This is your h function. And then this is the g function. So that they want you to do this. What's the limit as x goes to 0 of negative x squared? Well, that's negative what? 0 squared, which is 0. Is that true? And what's the limit as x goes to 0 for positive x squared? Well, that was 0 squared, which is what? 0. So you found the limit of your h function. You found the limit of your g function, okay? And they're both what? 0. What does that force the limit of f to be, since f is between h and g? That's also what? 0. So ladies and gentlemen, this also equals what? 0. And that we say, you always want to quote by the what? Squeeze theorem. Okay? It's a very classic theorem. It just doesn't work for everything you see in your life. Don't try to apply it. Keep your life simple. I'm now telling you, hey, guess what? All of these questions you're going to be able to use the squeeze theorem with. They're just testing you on really, can you read the theorem? The test is, can you read the theorem? Do you understand that process? An if, then. And what does x mean to be near? They just mean, x, they mean the limit, sort of mean a limit, but x is going to a, getting nearer to a from right or left. It's a test on, can you even read that? It's an if-then statement and apply the definitions. That's all. And, that's kind of what they have here for some of these. And you might say, well, what about x squared cosine 1 over x squared? Well, that's the same kind of thing. You say, what do you mean? How does that change? Do you guys know how similar sine is to cosine? They're very similar. Is that right? They're not the same function, but I'll start again by saying to you guys that, you know what? Cosine is also between what? -1 and +1. Okay? Is that true? You guys okay with that? And then, very similarly, it's not going to be any coincidence that they're going to use terms like this. If you guys can see, this is x squared, right? This is also x squared. They're not going to use x. They're going to use x to the 4th. They're going to use x to the 4th. They could use x to the 6th. If I thought about it, they can even use square root of x. I haven't thought of doing that, but they could. So why do you think that is? Because when you multiply the smaller function by an x squared or x to the fourth. We can change it. It doesn't change the direction of your inequality because x squared is assumed to be what? I mean, it's not assumed, but x squared will be positive. In fact, it will be greater than or equal to 0 for all x values. So that term right here doesn't change your inequality. You'll end up with negative x squared again, less than or equal to x squared cosine theta. I'm going to use 1 over x squared because that's the argument, which will be less than or equal to x squared. And again, you have, I don't remember, I guess it was with G, F, H, I guess. Was it G? No, H. I did it backwards, but okay. Doesn't matter. Smaller function, larger function, middle function. What do you guys know? They're asking you squeeze theorem questions. What does that mean? It means the limit as x goes to 0. And sometimes, if you read these books, they'll say the limit of this function equals the limit of what? This function. They are both what? 0. So here's my h. Here's my g. What does it mean then about the limit of the f function right in here? That's also what? By the squeeze theorem. And, you know, that's kind of what they want you to do with these, so you guys know. And then I can share with you guys, what else we want to share? Let's see, let's double check something here. I can say, similarly, you guys can do the work here. This is also 0, and this will be a 0, so you guys know. All right, you guys okay with that? They're all 0. And you guys will see that as you go through the same exact process as 1 is 2. Now, if you say, what about number 5 here? Well, this is kind of a nice situation. G, F, and then what? H. What's the limit now as x goes to 1 of the g and h function? Right? So you can say, okay, the limit as x goes to 1, this is of the function 3x plus 4. Is that right? What do you guys know about this function, 3x plus 4? It's a nice polynomial, isn't it? You use either, the book calls it direct sub, or you can say it's continuous because it's a polynomial. Oh my God, we're putting everything together? Yeah. And that becomes, that's equal to what? Isn't that 7? Okay. So that limit is 7. Let me go down over here. Apologize for this space issue. What about the limit of the larger function? And I'm going to change that because I find a typo. Change this to 6. All right. What do you know about this function here? X cubed plus 6. This is another what? Polynomial. Polynomials are the best functions. What do you get to do with polynomials? Plug in your value. And what do you end up getting? 1 cubed plus 6 is 7. The limit of the smaller function is 7. The limit of the larger function is 7. Then what's the limit of f? The middle function. It's also what? By the what? By squeeze theorem. You guys okay with that? That's what they want you to do. That's why I had to fix it. I got to fix that typo. Note to self. What do you think is going to happen in number 6? The smaller function less than the middle function less than the larger function. Let me get rid of all this so it doesn't distract us. All right, so here you go. All right, what's this limit question? This is the limit as x goes to 1. So let's find the limit as x goes to 1 of the smaller function, negative 4x plus 5. Another polynomial, nice and continuous everywhere. I could just plug in the value of x here, and I get 4 plus 5 equals what? That's 9. All right. Let's look at the limit of the larger function. X goes to negative 1 of the x squared plus 9. Okay. A nice polynomial again. Wow. I think that I already did the arithmetic in my head. 1 plus 8 is what? 9. So what does that mean about the limit for the middle function? It's 9. Why? By the squeeze theorem. And that's pretty much it, ladies and gentlemen, of what they want you to be able to do with the squeeze theorem, you know. But we want to make sure you guys know about it. It shows up in other math classes, that squeeze theorem. So, you know, you want to be able to say, yeah, I knew about the squeeze theorem. We did some work on that. And, you know, Mr. Judge even has documented all the work. He records the videos, and they're online, and and everybody else watches these videos. You guys don't know, some of your fellow classmates in your calculus classes, they want the links of these lectures. So they've come to me and said, hey, Mr. Judge, can you send me the link, please? I'm like, I can't do that because that's, I mean, I don't mind doing it, but then I might have 6 or 7 different, I have trouble sometimes putting the link into one class. I'm going to email 6 or 7 people every morning. Hard to do. You guys know what I mean? So some of those students have friends in this class. They send the links to them. That's what they've done. They're unlisted, meaning anybody can watch who has the link. They're unlisted. But they're go straight to YouTube. And that enables you to go back and watch any of these things. Do you guys ever do that kind of stuff? You go back and watch it? Maybe. Do you find it beneficial? Okay. I'm pushing this for other instructors throughout the district even. And this idea, it's very useful, I believe. But, you don't get, not everybody is what? Some people think it's just too much work for them to do. Instructors, I mean. Too much work. So the good news is I get to lecture them like I lecture you guys. What do I tell them? Isn't that why you're here? You're here to work, right? So I just don't save it I save it for everybody. It's like, hey, wait a minute, that doesn't make sense. You're here to work, aren't you? It's like, why would I want to work? Anyway, who really cares? And then you go, Mr. Judge, limits without